Alright everyone, welcome back. In this part of the lecture, we're going to talk about the mean value theorem. If you're a math major, this is going to be a very important theorem for you to actually see because it is extremely useful in higher level math classes. This theorem is used heavily to prove other theorems in classes like analysis, real analysis, complex analysis, and some other topological spaces as well. So without further ado, and by the way, this theorem actually comes directly as a result of Rolle's theorem. You actually prove the mean value theorem by applying Rolle's theorem. So without further ado, let me actually tell you what the theorem says. The theorem says that if f is continuous on the closed interval AB and differentiable on the open interval AB, then there exists a number C in the interval AB such that the following is true. The derivative evaluated at C is equal to f of B minus f of A divided by B minus A. Okay. Again, I'm not going to prove this theorem. You can find the proof of this theorem all over the internet or in the book. However, it is a very nice theorem, and it has a lot of consequences as well. Now, the mean in the name mean value theorem does stand for the average rate of change of f in this interval. So that's something to keep in mind. It's not that the theorem is actually a bad theorem, it just stands for the average mean on the interval. Right, so without further ado, let's do a couple of examples. Right, so let's say given f of x equal to 5 minus 4 over x, we want to find all values of c in the open interval (1 to 4) such that f prime of c is equal to f of 4 minus f of 1 over 4 minus 1. Well, first of all, the mean value theorem really is giving us the slope of the secant line through these 2 points. Now, this equation, this function up here, satisfies the hypothesis of the mean value theorem. Now, unlike the Rolle's theorem, we do not need the endpoints to be equal. We just need the function to be continuous on the closed interval and differentiable on the closed interval. This function is it's not a polynomial function, but it is continuous on the interval because we are working on the interval 1 to 4. Now, this function looks a little bit like this. It is shifted up 5 units, but it will look like this. It has a vertical asymptote at 0, and it is lifted up about 5 units. In any case, on the actual interval that we're working in, 1 to 4, there's no break on the graph. Okay, so it is continuous on this interval. It is also differentiable on that interval. So it's something that you should keep in mind whenever you see a rational function, especially the asymptotes. Because if the interval were minus 1 to 1, then we cannot actually apply the mean value theorem because the function then will not be continuous on that interval. All right. Now, because f is continuous on the interval 1 to 4 and it's also differentiable in this interval, we know that there will exist one number c in 1 to 4 such that the derivative is going to be equal to whatever this is equal to. So what is this equal to? Remember, the derivative of c is going to be equal to the endpoints by the mean value theorem, by the difference in the endpoints and the difference of the evaluation of the endpoint. So this is going to be equal to f of 4 minus f of 1. Well, what is f of 4? Let's actually do that on the side to make our work cleaner. So we have to find out what f of 4 is, we have to find out what f of 1 is in order to solve what the derivative is going to be equal to. So notice that to find out what c is, we don't need to know, or what the value of the derivative of c is, we don't need to know actually the derivative. We don't have to take the derivative. So anyway, we have 5 minus 4 over x. So f of x is equal to 5 minus 4 over x. So that means that when we evaluate at 4, we have 5 minus 4 over 4, which is 5 minus 1. Last time I checked, 5 minus 1 is 4. And when we evaluate at 1, we have 5 minus 4 over 1, which is 5 minus 4, which last time I checked, that's 1. Okay, so what we have here is that this is actually equal to 4 minus 1 divided by 4 minus 1. But 4 minus 1 divided by 4 minus 1 is just 1. This is going to have 3 over 3, which is 1. Okay, so now we know that f prime of c, the derivative, f prime of c is actually equal to 1. But by the mean value theorem, actually by Rolle's theorem, no, I'm not, but the mean value theorem, we now know that we are guaranteed a c on this interval such that this is true. Okay, now how do we find this c? Well, much like we did with Rolle's theorem, we take the derivative of f and we solve it for when the derivative is equal to 1. So let's do that. So what is f? F is 5 minus 4 over x. I'm going to rewrite this to make it a little bit nicer. This is 5 minus 4 times x to the minus 1. So that means that the derivative f prime of x is going to be equal to the derivative of 5 is 0, so that goes away. And then the derivative of negative 4 times x to the minus 1 by the power rule, we multiply that negative 4 by minus 1, so that's 4. And then we take away 1 from the top, so that's going to be minus 2. So this is going to be equal to 4 divided by x squared. So now that we have this, remember we were trying to solve for when f of c is equal to 1 from above. So what are we going to do? We're actually going to solve for when the general function is equal to 1. The general derivative is equal to 1. But now we know exactly what the derivative is equal to. This is simply equal to 4 over x squared. And we're going to find out when is 4 over x squared actually equal to 1. Now because we have an equal signs here and we have two fractions, we can cross multiply. So we have 4 times 1 is 4 and 1 times x squared is x squared. And if we take the square root on both sides, we have plus or minus square root of 4, which equals plus or minus 2. So x is equal to plus or minus 2. However, keep in mind we're working inside of an interval. So only one of those answers is actually going to be correct because we're working on the interval 1 to 4. So only the positive answer, x equals 2, will work here. Okay? So that means that by the mean value theorem, we can conclude that c equals 2 will give us the derivative of f being equal to 0. Okay, so whenever c is 2, the derivative is going to be equal to 0. Now, what this is basically saying, let's say again, we have this particular graph. What this is saying is that, let's say your graph looks like this, right? And you're looking at a point at an interval, like from here. Let's say this is A, this is B. Now notice, unlike on Rolle's theorem, the A and B are not actually equal. Okay, they're not actually equal, but we can actually still find a C such that the derivative is equal to 0. In this case, the derivative was equal to 1. Actually, that's a mistake. Equal to 1. So now we have a slope of 1 line here. This is a more general case of Rolle's theorem. All right. So this is how your tangent line will look like. All right. Let's do one more example. This one is more of a word problem. So there are two police cars equipped with a speed gun, parked 5 miles from each other on the highway. Okay. Now a truck passes the first patrol car and its speed is clocked in at 55 miles per hour. Now, 4 minutes later, the truck passes the second police car and its speed is clocked at 50 miles per hour. Now, what we are asked to show is to prove that the truck must have exceeded the speed limit of 55 miles per hour at some time during the 4 minutes. Okay, so let's actually do a quick picture to see what's going on. So we have one police car. Let's say, the car is like here, right? It's parked on the highway. And then 5 miles down the road, you have another police car also parked down the highway, right? Now these police cars are 5 miles apart, so the distance here is 5 miles. And then we have a truck I cannot draw trucks to save my life. Then we have a truck this truck will actually fall in half. Let me add another wheel there. Then we have a truck that's traveling between the two vehicles. All right, let's actually introduce some variables here so that we could begin to talk a little bit about this problem in a way that makes more sense. I'm going to let the variable t represent time, and t equal to 0 represent the time when the truck passed the first police car. That means that at this point right here, t is equal to 0. The truck passed the first police car, the t is equal to 0. That means that 4 minutes later, when t is equal to 4, the truck is going to pass the second police car. This is what was given in the problem. 4 minutes later, the truck passed the second police car. Now, the time when the truck passed the second police car is actually given by the following. We know that it is 4 minutes, but we're talking about miles per hour as far as the speed of the truck is concerned. So we have to actually turn this conversation into hours instead of minutes. We're talking about minutes before. So how do we do this? Well, there are 60 minutes in 1 hour. So what we really have is 4 minutes of 1 hour, which is really 1/15 of an hour. So now we're comparing apples to apples. Now, if we let the function s be a position function, representing the distance in miles that the truck travels, we have that s of 0 is equal to 0. That's the initial time when you've passed the first vehicle, the first police officer car, and actually I wanted to say s of t here. Okay, this with respect to time. So s of 0, you just passed the first car when t is equal to 0. So when t is equal to 0, you're right here with the first police car. When t is equal to 4, you're right here with the second police car. In any case, we now know what time the truck passes the second police car. It's at t equals 4, which is the same thing as t equals 1/15 of an hour, since we're talking in hours. So when s equals 1/15, when you plug in 1/15 for t into s, we get 5. The reason why we get 5 is because the distance between the first police car and the second police car is 5 miles. So here you have traveled 0 miles, and when you get up to here, you travel 5 miles. All right, now we actually have everything we need to actually apply the mean value theorem. First of all, let's assume that the position function s of t is continuous and differentiable. Okay, let's assume that this is true. If this is true, then we actually can apply the mean value theorem. How do we do that? Well, the mean value theorem says that f prime valued at c is equal to f of b minus f of a divided by b minus a. We know what our interval is. Our interval is 0 to 4. Okay, but we actually, remember, we switched the 4 because that was in minutes to 1/15th, so in reality it's 0 to 1/15th. We're talking in time intervals here. So what we have here is really that f prime of c is equal to s of 1/15th, because this is our function, minus s of 0 divided by 1/15th minus 0. Remember, our interval is 0 to 1/15th because we're talking about hours. If not, it would have been 0 to 4 had I kept it in minutes. Now, I said up here that s of 0 is equal to 0 and s of 1/15th is equal to 5, so I could simplify this more. S of 1/15th is equal to 5, s of 0 is equal to 0, and then in the bottom we have 1/15th minus 0, which is just 1/15th. So what we really have here is 5 minus 0 is 5 over 1/15th. If you multiply with the reciprocal here, you have 5 times 15, which is equal to 75. So what I'm doing here is 5 times 15 over 1, simply multiply by the reciprocal of this, and that's going to give us 75. But remember that we're talking in terms of miles per hour here, because this right here is given to us in terms of time, and this right here is given to us in terms of miles. So this is 75 miles per hour. So we have that by the mean value theorem, the truck must have been traveling at 75 miles per hour at some point during the 4 minutes. Because remember, the mean value theorem guarantees us that this happened. Okay, the mean value theorem guarantees us that this happened in this interval, if we assume that the function s that I wrote down is differentiable on the interval. Okay? So this is another type of way in which we could see the mean value theorem be applied. I think this is a pretty nice example for those of you who drive. It'll be, I always find it kind of funny, like if I was a police officer or if I was like a traffic agent or something like that, and I had to give people speeding tickets, this would be a cool way of proving that they actually had to have gone faster between, let's say, where I was and my colleague was down the road, by using some calculus. I think that would be pretty funny if you get a ticket like that. I mean, it's probably not gonna be funny. You're gonna have to pay a pretty ticket, but if I wasn't paying the ticket, I would probably laugh at that. Anyway, there's actually an alternative form of the mean value theorem, which I wanted to show you, which is sometimes very useful. And I'll actually show you how you get it. So the mean value theorem, I'm not going to write down the statement down, everything that it says, but it says this. The derivative evaluated at c is equal to f of b minus f of a divided by b minus a. So another way that we could write this, well, let's multiply both sides by b minus a. So that means that these cancel out, assuming that they're not, assuming that b minus a is not equal to 0. So we're left with f of b minus f of a being equal to b minus a times f prime of c. And now we could add f of a on both sides. And we have that f of b is equal to b minus a times f prime of c plus f of a. This is a very useful form of the mean value theorem as well, because now we know how to describe the value of the endpoint in the function in terms of the derivative. And this comes this turns out to be actually very useful when you are, again, trying to prove things in other classes. That is it for this section. Thank you for your time and attention.